Welcome to this video on the mathematics of choice. Today, we will explore the fascinating world of permutations and combinations, uncovering the underlying principles that govern how we count and organize possibilities. Imagine you have a four-wheel number lock, but you only remember that the first digit is 7. Trying to count every potential sequence manually is tedious, error-prone, and unsustainable. We need a better way. This is where the fundamental principle of counting comes in. If one event can occur in m ways and another in n ways, the total number of combinations is simply m times n. This simple multiplication reveals the hidden structure of choice. To scale these calculations, we use factorials. A factorial, denoted by an exclamation point, is the product of all positive integers up to n. It acts as a powerful multiplier for counting arrangements, with the crucial rule that 0 factorial equals 1. When we talk about permutations, we are looking at arranging distinct objects in a specific order. If we have n total objects and want to fill r vacant slots, the number of choices decreases with each step. The formula for a permutation, NPR, represents this process. It generates the total factorial cascade for all objects and uses division to filter out the unchosen items, giving us the precise count of ordered arrangements. Let's see this in action. Forming 3-letter words from the 6 letters of number gives us different results depending on whether repetition is allowed. Order matters, and as you can see, the math changes accordingly. What happens when objects are identical? If we arrange the letters in the word root, we must divide by the factorial of the repeating objects to remove redundant variations and collapse the permutations back into reality. Sometimes, the internal order doesn't matter at all. For example, in a room of 12 people shaking hands, X shaking hands with Y is the same as Y shaking hands with X. Here, we are selecting, not arranging. This brings us to combinations. To find the number of unique groups, we take the permutations and divide by r factorial to erase the importance of internal ordering within the selected group. For instance, if you need to form a committee of 3 from a pool of 5, the combination formula tells us there are 10 possibilities. We can further refine this to select specific subgroups, like choosing 1 man and 2 women. Combinations also reveal a beautiful symmetry. Selecting R objects is mathematically identical to rejecting the remaining n-r objects. It's an elegant way to simplify complex choices. To summarize the architecture of choice, use permutations when the order matters and combinations when it doesn't. Understanding these two frameworks allows you to solve a wide variety of counting problems. Sometimes you need to blend your tools. By grouping items into a single block, you can apply permutations to the macro-level arrangement and then again at the micro-level within that block. We have synthesized the blueprint of choice. Whether you are using permutations, combinations, or the fundamental multiplication principle, factorials serve as the engine powering these mathematical discoveries.